Okay, the last piece of this is data extents. So the original plan, and this is still the case, is to deal with, to do away with this idea of bookended, well, not do away with, but change how we deal with bookend extents. So, what are bookend extents? This is where, we allocate an extent, say it's 128 megabytes, and then we write into the middle. And so we end up with 4K, and then, this part left over. What we do here is we call it bookending, and it's called bookending. So this original extent right here, we have a reference for it. So say it's in this, subvol A, I know, 300. So we have a reference to, say this is offset 0. So we say, offset 0, 128 megabytes, and it belongs to root A, I know 300 at offset, we'll say logical offset is 0 too. Offset, yes. Offset 0. All right. So what happens when we do split this 4K, what we end up with is what the code does is it says, okay, new file extent, increment, or do we increment for this side? No, we increment for the other side, because this is still the case. We create a new file extent, and we set the offset to whatever this is. So say this is right in the middle, say this is 64 megabyte. We say the offset here is like 64 megabyte plus 4K, and we say the disk byte number is 64 megabytes plus 4K. And we add a reference. We add a reference, but we have to do it for the original offset. So we take the disk byte number and subtract the offset to get the original byte number, which is 0. And so now we have root A, I know 300 offset. Oh, no. Do we do to yeah, sorry. I can't even fucking remember what we do. Anyway, what happens is we end up with two references. That's long story short. We have two references now. Two references. Two refs plus the original ref for this. What does this mean in practical terms? It means that the original 4K that was right here, because this 4K is allocated somewhere else, but this original 4K is wasted, essentially. It cannot be accessed because we have to overwrite this entire extent before we will free it. So say if we overwrite from here to here, we'll drop this whole extent and we'll go back down to 1 ref because we have this. And now we have this range right here, completely not being used, but it's used in that it can't be reallocated to the rest of the file system. In practice, this doesn't really hurt us, okay? Because in practice, we don't do this too often. There's not a lot of overwrite workloads. However, there are two pretty important overwrite workloads, and they are vert images and databases, some databases. MySQL, that sort of thing. RocksDB does something different. RocksDB is append only, which is awesome for ButterFS. RocksDB works really well, so if you use MySQL with MyRocks as the backend, it's awesome. But if you use Postgres or InnoDB, I guess is the traditional MySQL backend, they suck. Super duper sucks. It's partly because of this, partly because of other things. But vert images are really, really bad because they will go and they'll pre-allocate, big chunks. So this is 8 gigabytes, and then they'll just randomly write in here because you never fill up a vert image. But like as they're like overwriting, it's like literally taking up this much. So like a vert of 8 gig vert image can, if you do it right, can take up close to like 16 gig. Not exactly, because you'd have to like overwrite everything except like sector size in each extent. With 128 meg extent sizes, you know, whatever 8 gig divided by 128 is, and then times 4K, that's how much you're going to have to not write. So it's that minus 16 gig. But it essentially comes out to like 15.5 gig or whatever. It's a lot of fucking space. You don't expect to take that much space up. It's not great. Like I said, we tend not to have this problem because we recommend that people use no data cow, which means that instead of copy on writing this section, we just fucking write right back into it. Whatever, we don't care. But the problem with this is no csums and no compression. And is there anything else? Probably no encryption when we have that, but that doesn't really matter right now. Is there any other drawback? Oh yeah, it still hurts. Still hurts if you snapshot. So no data cow is no data cow until you have a snapshot, and that snapshot demands copy on write. So like you can snapshot your vert, your var run images, or I don't know, wherever libvirt stores its shit. If you snapshot that, you're screwed. You lose the no data cow property. I mean, you lose it the first time. So like if you cow this chunk and then you write back into it, you'll still write. You'll not cow the second time, but the first time you'll cow. So you could still potentially waste 16 gigs. In practice, nobody notices this. But it does come up occasionally, and people get real angry when you tell them about it. Why do we do this? Because it's fucking easy. We track space based on offset length pairs. So, if we just always keep track of what the original offset and length is, we can just like add and remove references at a whim, and it makes the reference counting really easy. So like I said, all of this was done for simplicity's sake. Btrfs was the first file system to do something like this. We really stuck to the original design of the B tree, the copy on write B tree, because we're not academics. It was a good idea on paper. And it worked out pretty well. Like, yes, it has these kind of corner cases that suck super bad, but all in all, it works really well, and it's easy to wrap your mind around. Well, relatively easy to wrap your mind around. Unfortunately, this drawback has become more and more pronounced as the years have gone on. So, my solution to fix this is to no longer use bookends in the normal case. Now, for things like compression, we still have to use bookends because, if you have like a, 128 meg, just, zeros, right? You just have zeros. This shit will compress into, a 128K, just theoretically, compressed extent. But we have to decompress this whole thing into the original extent. So if we like right in the middle of this, we can't just like free a little chunk in the middle of a compressed area because the entire compressed thing is required to get back the original data. I can't just like arbitrarily say, I don't need this like 4K chunk in the middle of 128K compressed extent, because I could have like data in there that's necessarily for decompressing like the rest of it. So bookends will still exist for compressed, and maybe encryption. It depends. I don't know what Omar is doing with encryption. But for compressed, it will stay. But again, with compressed, we have a limit of 128K compressed extents because we can't be decompressing 16 gigs into memory. It's not going to be super awesome. So we limit, and it's also like CPU costs and that sort of thing. So we limit the size of extents, of compressed extents, to 128K. So the most you're ever going to waste is 126K per extent. 126K for a 128K thing. So like if you have, certainly if you had like a really big file and you're like only writing writing 124K. If you write 124K in every chunk, you're gonna like still get the same behavior. But in practice, in the real world, it's not going to be as bad as with normal extents. Normal decompressed extents is what I mean to say. Yeah. Anyway, so how's this going to work? By making the extent tree like infinitely more complicated, unfortunately. So right now, the file extent, and let me pull it up on my screen to make sure I say this right. Okay, so the file extent has disk, byte number, disk, num, bytes, and it has offset. So these two are important. Like clearly this is like where it is on the disk, the logical offset on disk. Num bytes for normal extents is going to be the same as bytes, but like if it's compressed, this is where you'll see like 128, but like because it also has num bytes. Or what is that, RAM bytes? Yeah, it has RAM bytes. It's RAM bytes. And this is because, like for compression, like 128K could be this, but this could be like 4 megabytes or whatever. But this is the part we care about, right? Because this maps to the extent tree. So currently it is disk bytes number minus offset. And then it's, I think disk num bytes always stays the same. Maybe I'm wrong. I'd have to look. No, I think it doesn't. So then it's like, disk num bytes plus offset is like the actual length. I think that's how it works. I could be fuzzy on this. Anyway, you get the idea. The offset says where the original one is. This is how it currently works. So we get this, and then we mess with reference count for this byte number offsets for the roots and inode and like logical offset in the inode. So like, if I read, if this is offset 1 in the inode, that's what that value is going to be in the reference count. What I want to change is that we do away with this. So in my previous example, 128 meg extent, 0, 128 meg, write to 4K at 64 meg, it's 4K length. In my previous example, you ended up with 2 references for this byte number and 1 reference for this byte number. Instead, what I will do is I will drop a reference for this range, and I will add a reference for this range and this range, and then I will add a reference for this range. This looks super fucking weird because the way delayed refs run is I will add these first, and then I will I'll add all of these first, actually, and then I will drop this. So how does that look? It looks like we will now have overlapping extent references in the extent tree. This gets a little complicated. This is why we just did bookends, because it's less weird with the reference counting, but it has this kind of it has the space wasting drawback. If we don't want to waste space, this is what we have to do. So what I will do is I will add reference, add ref for 0 to 64 megabytes, sub A, I know 300, logical offsets 0, and I will add ref of 64 meg plus 4K, and then 64 meg minus 4K for this one, and this is this guy. And then I will add ref for wherever this thing ends up. I don't know, let's say it's like right here, like on the thing. So it's 128 meg and then it's 4K. Adds that guy. And then drop ref for 0 to 128 meg, which is the original reference. So we'll drop that reference. What does that look like on the extent tree? It looks really bad and complicated. So what will happen is every extent modification will lock that area. So everybody knows Btrfs has range locking. So for this 0, or for this section 0 to 64, we'll lock 0 to 64 and we'll modify our extent. And then for this guy, 64 meg to plus 4K to 128 meg, we'll lock that extent. And for this guy, we'll lock this extent. And then when we go to do this guy, we'll lock this extent. This is important because if one thread is running the delayed ref for this guy, and then this guy is running a delayed ref, we're going to have problems. This gets kind of awkward, because what we will do, we don't care about additions. Well, we kind of do, but we don't. Because at this point we know that we've gotten the space and we've freed it up or we've removed it from the free space tree. We'll free it up once we add it. Right here is, what we will do is at drop time, drop time, remove range. Then check for holes. This part is ugly. And this is why we had bookend extents, because this is essentially what you end up having to do. So now I've dropped 128 meg. I need to scan from 0 to 128 meg and see if there's any holes in here. So I will have added my 2 chunks, and I see that there's a hole right here. I will add free space for for any holes. In reality, what I'll actually do is pin. So because we can't actually use free space in the same transaction, I'll just pin this range, and then when the transaction commits and we unpin, the space will be added. Right. That's how that's going to work. This is the normal case, no snapshots, no nothing, just ye olde reference counts. This is complicated, but we've had enough people kind of complain about the worst case scenario of wasted space that I think it's worth it, because because we're going to drastically reduce the amount of references in an extent tree and also increase the amount of extent trees. So the more complicated operation where we have to like lock an entire range and like scan the range and check to look for holes, that'll be less painful in the new scheme than it would be in our current scheme, because in our current scheme we would potentially block out any other delayed refs from running just in like the mechanics of searching down the tree to find this thing. This will greatly benefit things like vert images or databases, which are going to be relatively large and kind of occupy entire block groups with their data anyway. So it's not like we're going to have a lot of threads modifying the same block group. Or sorry, we could have a lot of threads. We're not going to have a lot of different files occupying the same block group. So you're not going to have like me writing to a Vim file while a database is running and have to deal with the contention of a Vim file that wants to fsync, for example, and while a vert image is doing this complicated action. It's potentially possible, but in reality it's not going to happen that often. And that being said, I could be wrong. This could end up sucking super bad, but I don't think it will. So the next thing is, how does this work with snapshots? Snapshots make this a tiny bit more complicated. Snapshots make this more complicated in my new snapshotting scheme. So what happens when this 128 meg chunk is shared? Well, every extent item has a generation. For when it was created. So because of that, we can use the same scheme to determine whether or not a particular file extent is shared. Well, we can figure out its maximum counts of the shared ones. So what we do is the same scheme as what we do with metadata. However, before, in the example that I gave, where we have 0 to 128, and we write into the 4K, and we free this whole fucking thing up, and we add in these chunks, this part is the part that changes. So instead of doing the free, we do what we would do with the snapshot with metadata blocks, is we add a delete record for 0 to 128 megabyte. So the first time we modify this guy, we determine that it's shared, because we see the generation. Say its gen is 9, it was snapshot at 10. We know it's shared. We say it was snapshotted once. We know the max count is 2. We add a delete record for this guy. So we cow down from the original. Say we cow down from the original subvolume. We add a delete record for the original subvolume, and then we cow down from the snapshot. And we add delete record for the snapshot. And that's when, drop ref equals 2. And that's when we trigger the actual remove. And then it does the same dance as over here, where we add reference, the adding reference stuff will still happen. So we'll still add a new reference for this section and this section and this section. All of the additions will be the same. It's just the deletion doesn't happen until we get a drop ref of 2. And so once the drop tree has the correct counts, like an equal count for the max count, we know we can free this entire range up, and then we'll go and free the entire range from the extent tree. And then if we have poked many holes in here, like the entire section will end up cleaned up, and the whole, like if this is a hole and this is a hole, like anything in this area that's no longer in use by the other roots will be freed up and returned to free space. So this it seems like waste, but it's not, because if it's being referred to by other trees, then it's being referred to, and we can't free it, right? So like if the snap like modifies the first section, but orig modifies this section, theoretically, like the whole thing is still being referenced. It's just being referenced in different places. So like, yeah. So even though it's like at this point we would issue the drop, because so we do this, and this drops for 0 to 128 and adds this section, right? And then the second time this drops 0 to 128 and adds this section, and that's the point at which we'll do the 0 to 128 drop. But since it's still referenced, you won't actually free any space. But if you again, if I didn't do this or whatever, it's still being referenced by orig, or I could even overwrite it completely and snap a, and still be referencing it in the orig, so it's not wasted. But this is how we combine. If the extents can be shared, we must go through the drop tree. And the drop tree will not split, again, because we're referring to the whole extent in the shared blocks. So the drop tree will never have ranges that overlap. The extent tree will. And again, the extent tree is purely for data now. It's no longer for metadata. We'll only be tracking data. The reason for this, and the big reason for this, and the reason why I don't just do a drop tree, is reflink. You can have reflink, I could have a 128 meg thing, and then I could carve out chunks and share it to myself or to other files. And so we kind of need the heavier handed extent references for data. But that's, again, that doesn't really hurt us that much, because data doesn't get modified too much. Clearly it does, but it doesn't have the explosion that metadata does. You modify data, you're going to have to modify metadata. That's how it is. Those two operations go hand in hand, and they're never going to explode out in the number of items that we have to modify. Yeah, that's pretty complicated. Sorry, this shit is complicated. Is that all of the? I gotta pull up my list of things that I wanted to talk about. All right, that's everything. That is all of the changes. I had a question about scrub. I was like, for scrub, why, oops, god damn, I can't type. Why, not use free space tree for scrubbing. So the argument was that we could use the inverse of the free space tree to figure out what blocks were in use for scrubbing. Because we have the data, we have extent references for data, Like I could still use the extent tree for data. This is purely for metadata. Like metadata is where we don't track anything, which is why I said we have to walk down trees in order to scrub metadata. So why can't we use the free space tree, the inverse of the free space tree, to figure out what's allocated in metadata chunks? The answer is we can. So we could definitely use that because we know our node size, and so we can just say like, every 16K offset or node size or whatever is a block. So we could read it, checksum it, and find the owner and validate the block. We can do all of that, yes. The problem is if something goes wrong. So if we read a block and the checksum doesn't match, we can't trust the owner ID, the header, and the owner in the header. And so we have no idea who that block belongs to. And so we can't really do anything. This is semi-okay for our RAID stuff, which is where scrub really kind of matters. So like if we have mirrors or, multiple copies or whatever, and, one copy is fine, other is broken. So from here, we can use the find copy to figure out who the fuck this guy is and like rewrite the second copy. Like that's easy. The problem is if they're both broken, we have no idea who it belongs to. So we don't have to, but it makes more sense to read down from the tree blocks, the trees themselves in this case, because in the case that we find an error that we can't correct, we can't tell the user where the fuck the problem is. And we would have to go and rescan all the trees anyway. And that might be desirable. It might be desirable to err on the side of speed over correctness, because like if we find a problem, we could just go back and rescan, because chances are we won't find problems. But then again, if you're running a scrub, you're probably expecting to find problems. So it's just one of those trade-offs. I decided that it's better to read down from trees so that at least when we find something that's wrong, we know who it belongs to and we can tell the user the appropriate thing. Was there another question? I don't think there was. Let me double check. Oops. Holy shit, I messed up. Oh, right. This is the question I had for myself that I had to work out. Modifying, and this is a little bit different, snapshots before commit. So what do we do here? The ugly truth is that we do actually modify the snapshot like immediately after taking the snapshot. We don't modify the snapshot. We modify the original tree immediately after taking the snapshot, because what we do is we copy the block for snapshot, and then we add link to snapshot in original root. Now, the link could be in a different subvolume, but it tends to be in the same subvolume. Anyway, so what this thing means is that we will say, gen 10 was the snapshot, and then we'll like immediately modify this guy. So this is A, and this is A prime. And we will like immediately and A prime points at these guys. Oops. But then we will immediately modify this guy to add something. So then we get this. And this will still have gen 10 because we do it before the transaction commits. So which means that this guy, with no other knowledge, will appear with my original scheme that I described. It will appear to be shared by A prime because it has 10 and our snapshot length is 10. This will work out correct. This block right here, its reference count will be correct because we'll do the correct thing. We'll see that it's 10 and therefore add a delete record for A. So his reference count will be right, but this guy's reference count will be completely fucked. The way we are dealing with that is a sub trans ID. This is lovely. We don't have this in the header, and we don't need it in the header. We need it in the delete record, and also we need it in the snapshot record, because the other fucking fancy thing that I want to do is I want to snapshot without commits. This is something Felipe brought up, but I also want to do this, or we don't even really like fucking need this. Like, we could still require a commit, but right now you can get a snapshot with you could snapshot, A into, A prime and A prime prime in the same transaction, because we queue this up and do them in bulk at transaction commit time. So we can actually do this twice. So we could snapshot this, we get this guy off to the side for the ref, and then we fucking do the snapshot for this guy, and we add yet another fucking ref over here for the A prime prime. So A prime points at this. Sorry, I'll do this. And A prime points at this guy. A prime prime points at this guy, and A now points down here. What do I do for this? What I do is I increase a sub trans ID for every snapshot. So first snap for A is gen 10 sub gen 0, and then we do A sub trans ID plus plus, and then when we do this guy, if we cow during snapshot, we add a record for its sub trans ID. That way, if we do just one thing, when we go to cow this guy, if we only did it one time, like we do over here, we got to look up his trans ID or his delete record and see that its subtrans ID is 1, and so that we don't include this guy, because when we add snapshot records, we have to record the subtrans ID record. Include subtrans ID. So when we go to look this guy up, we'll say, trans ID 10 sub 1. And so when we walk through the graph up here, this will be trans ID 10 sub 0, so it's not shared, so it's still just 1. And then if we have a second guy, this one would be trans ID sub 1, and so we know it's shared by these two guys, and we would have a delete record for A when we cowed, and then this guy would be trans ID 10 sub 2, and we know that, as long as there was no other transaction, there's no other snapshot over here, so we know that it's only 1. I want to avoid doing a lookup of the delete record at all costs. I don't want to do it while we're cowing. So I will introduce a new flag. New header flag. Something like Btrfs sub trans ID. And this way we know that we have to look it up when we cow this guy to decide if it actually is shared or if it's not. If it's not, then we know we can just fucking free it. This is fine. We only have one flag in use in the header right now, and this is just an optimization to keep, because this doesn't happen that often. Like I said, we do it. I mean, it does happen often. We add the fucking link, and so things get modified. But like, that's the only thing that happens. So there's only going to be like a path to a leaf that has this flag set and a snapshot. So, you know, at most 8 blocks that have this set out of, you know, thousands. So for 8 blocks, we might have to do an extra lookup on cow. But for the rest of them, we won't have to. But theoretically, we don't have to do this. We could just always look up, but I would if we were shared, but I really would rather not. I want to avoid doing other tree lookups in the fast path, in the normal path, if possible. So I'm going to use this to shortcut. If this isn't set, we don't have to think about it. Otherwise, we do. And this will allow us to, with this sub-trans ID scheme, it'll allow us to be fucking fancy. So we're kind of limited in the transaction commit and the amount of snapshots that we can create. In the grand scheme of things, this isn't really a limiting factor. Like, you can create thousands of snapshots relatively quickly, but kind of like that nice fancy like sticker on the front of the box for Btrfs, like I would love to be able to make 1 million snapshots in a second or something like that. And this is kind of what would allow us to do that, is having these subtrans IDs. So yeah, I think that's everything. I might do another video if anybody has more questions, but that's everything. Hopefully I can get all this code written in the next few weeks, and we can start getting it tested and get it rolled out everywhere.